All right, so this is an example of a solid revolution, and this one's a little more complex than the ones that we did in class today because they're asking us to find the region enclosed between these two graphs. And part A is asking us to find that volume when it's rotated about the x-axis. And part B is asking us to find the volume when it's rotated about the y-axis. So let's go ahead and explore this. So the first thing I'm going to do is I'm just going to sketch a little graph so you guys have an idea of what this looks like. So this is not going to be accurate by any means, but it'll give you a good idea. So this is y equals x. So basically all the coordinates are 1, 1, 2, 2, 3, 3, 4, 4, and so on. Okay? And then y squared, y equals x squared, looks something like this. Okay, so what you should probably be thinking is, where do they intersect? Well, they intersect at 0, 0, okay, and at 1, 1. And if I wasn't sure about that, that says 1, 1, okay, I could go ahead and set these equal to each other, right, and then solve for x, okay. So, right, so this is how I would do that. And I factor x out, it's minus 1. So I have a value x equals 0, that's this, makes the whole equation 0, and x equals 1. Okay, so that kind of tells me where they intersect, or I could know that from here. So basically, we're looking at this region in here. Oops, not that one, that one. Let me change this back so you can see. It's just a really small, major fail. But you can kind of see this little purple region in here is what we're looking at. So we're going to be looking at that as we rotate it around the x-axis. So let's go ahead and get started. So we're going to basically find the integral from 0 to 1 of pi times f of x squared. So we have to do the upper bound first, which is x, okay, squared, okay, and then we could do the lower bound also from 0 to 1, which is pi times x squared, and remember we're taking the integral, so we need to tack on a dx here, so that's telling us the width of our, of little, if it's 2D, the little rectangles we're making, and these are the discs here. So, and again, we're trying to get as many discs as we can to be most accurate. So let's go ahead and integrate this. So as I told you in class today, we can go ahead and pull the constant pi out front. So all we're integrating is the x squared because pi is not going to change. It's going to be the same. So we could end up with pi times 1/3 x cubed, right, from 0 to, oops, I wrote that backwards, from 0 to 1, okay, and then here I could do the same thing, and if I simplified x squared to the power of 2, I end up with x to the 4th dx, okay, and then I can integrate this, and I end up with 1/5 x to the 5th, okay, from 0 to 1 again. So I'm going to go ahead and plug in 1. And I know it's shocking, I get 1/3 pi. And I'm going to take away what I get here, which is 1/5 pi. So if I were to subtract these, I would need to get a common denominator, right? So I could do 5/15 pi minus 3/15 pi. Okay, so my volume around here, if I were to rotate around the x-axis, so we're going like this, okay, and we're making a little circle, like, okay, is 2/15 pi. Alright, so that's when I rotate about the x-axis. Now, if I rotate about the y-axis, we end up with something a little different because instead of kind of rotating like this and ending up with a shape that looks something like this. See, I'm really bad at drawing 3D things. A bunch of little, it's not my strong point here, circle. These are like little solids. This would be like the solid, sort of. We're actually going to be rotating this way, okay? So that changes things a little bit. So let's go ahead and look at how that happens. So, alright, so let's go ahead and do part B now. So the biggest difference with part B is that instead of integrating about the x-axis, we're actually integrating about the y-axis. So basically this little part is going to make a circle this way, and it's going to look something like this. So you can see, well, this is a really horrible drawing, but you can see the volumes look different. So the biggest change is when we integrate about the y-axis, we have to have everything in terms of y. So instead of having this, right, or which is equivalent to, or your book sometimes writes it like this. That's a pi, by the way. Pi 1 squared dx, right? These are the same thing. Instead of having it like this, what we really need to be doing, you'll notice our bounds are different because we're looking at the y values instead of the x values. We still have pi, but instead of timesing it by y squared, we're going to be timesing it by x squared with respect to y. Okay, so this is the difference. So now we've got to have everything solved for x, or x squared. So let's get to it. Okay, so basically I'm going to write, I'm just going to write two integrations. Again, you could write this as a singular one, but I think that it's easier to do it separately for these. Okay, I'm going to come back up here. Okay, so basically I'm going to pull my pi out like we had discussed in class because pi is a constant and it's not going to change. So now look, I'm looking at the x values. So my x values in this particular problem, okay, well my lines are looking a little sloped here. They happen to be the same values because y is 0 here and y is 1. X was the same thing. So we're looking at the y values, not the x values. So the horizontal instead of the vertical, they just happen to be the same as the values in part A. So you'll notice that we have A and B for the original and C and D. This tells you that they're different values we're looking at. Okay, and now we're going to go ahead and look at the x squared. So we have to have everything in terms of x. Well, this one's easy because x equals y. So we end up with y. Okay, and x has to be squared, so we're going to square it, dy. Okay, and let's go ahead and integrate. So when I do that, I get 1/3 y cubed. Right, actually do this from 0 to 1. Okay, so there's that one. But now this is where the trickier part is, okay? It's not really that tricky, but it's a little different. So in this second problem, I already have x squared. And I'm substituting in whatever x squared equals. So all I'm going to substitute in here is y, dy, okay? So when I go ahead and integrate this, I end up with half y squared, okay, from 0 to 1. So I'm substituting in just y because x is already squared here. And I'm doing just a straight substitution. I don't have to do anything fancy there. Alright, so how we approach this is a little differently in terms of finding the volume than we did before. So, well, sort of different. So you know how on this one we said the upper bound subtract the lower bound. That's how we did area, and that's how we did rotations about the x-axis. But here, when we're doing revolutions around the y-axis, what we need to be thinking about is the outer radius, which would be this part, minus or subtract the inner radius. So this round this part is going to be the outside of our curve. This is what's going to be going around, okay, making that's going to be the widest part, and this part is going to be the inside, right? So it's kind of, we're going to basically say outer minus inner. So in this case, this would be our outer, and this would be our inner. So when we do our difference, we're going to say outer minus inner, okay? So when we substitute 1 in here, we end up with half times pi, okay, right? So I put 1 in, minus, and I'm going to put 1 in for y here, and we get 1/3 pi. And if we get a common denominator, we end up with 3/6 pi minus 2/6 pi, which means that our area is 1/6 pi. Okay, so you'll notice that even though our bounds were the same, our upper and lower bounds, because we're rotating around the y-axis, we ended up getting different values than when we rotated around the x-axis, and we will cover more of that in class tomorrow. All right, enjoy your night.